Many thanks for this opportunity, for the invitation to India, my first visit to India. So I hope that at the next visit, I will also have a picture of Bangalore here as a possible future site for a major accelerator facility. Anyway, I was asked to give an accelerator overview. And I think I took material from many colleagues. Some of them are listed here. And I thank Rohini and Chapo. So I like to cover different topics. General overview of accelerators, particle colliders, next generation, next, and next generation high energy machines, advanced accelerators, brief outlook to the future, and then I conclude coming back to the next generation of machines. So this is just general remarks on accelerators in the 21st century. Worldwide, as is from a few years ago, there were more than 30,000 particle accelerators. Less than 1% is for basic research, 5% for applied research, 35% for medicine, and 60% used in industry. And accelerators are well-known engine of discovery. There was a study by Haussaker and Alex Shaw, who showed that about 1/3 of all Nobel Prizes in physics since 1939 were connected to particle accelerators. And also there are advanced scientific tools, 18 synchrotrons and 8 FEL-based light sources in operation in Europe, also neutron source, etc. And also from these machines, there were many more Nobel Prizes, and they had a strong impact in all scientific domains. They're also providers of quality healthcare. As you can see here, more than 10,000 accelerators for radiotherapy installed, accelerators for radioisotope production, and also particle therapy centers. And they are used for cutting-edge industrial developments. Okay, this is a more detailed assessment that was published in the frame of the European UCAD project that you can download here, 100 pages or so, assembled by Rob Edgecock and Angeles Fosgolf. And you can see different applications and energies and beam currents, etc., and references. Okay, in 1930, the first cyclotron built by Lawrence had this size. It fitted into the palm of a hand, 11 centimeter diameter, and it produced 1.1 MeV protons. Nowadays, we have the Large Hadron Collider. It's a 9 kilometer diameter, so it's significantly larger, but also the energy of the protons increased tremendously to 7 TeV. This development of energy you can also see on this plot for high energy colliders. There are different types of colliders. In Large Hadron Colliders, we had only a couple of hadron colliders, actually only 5 in the history so far, 3 of which were at CERN. There's one electron hadron collider, Hera, and then there's also ion colliders, LHC and RIC, serve both as proton colliders, also as ion colliders. And then there are a lot of E+, E- electron-positron colliders, and also early on electron-electron colliders here, indicated in blue. And the energy was increased thanks to new technologies, especially to the use of superconductivity. So Tevatron and RIC are colliders with superconducting arc magnet systems. Petra Tristan Lab 2 use superconducting RF systems, and Hera and LHC use both superconducting magnets and also superconducting RF. So the advances were made by new technologies and new materials, in particular, in this example, superconductivity. There are other technologies, and in particular, Swapan played a big role in choosing other technologies. Here are more colliders, including the factory machines and proposed future machines. Again, energy, center of mass energy versus time over almost 100 years, 90 years here. And Swapan came into the game around 1980, and basically everything above a few GeV and above, and starting in 1980, he contributed to stochastic cooling of bunch beams of antiproton heavy ions, now used at RIC. Development of asymmetric B factories, highest energy hadron and lepton colliders. So when he was director of the Kirchhoff Institute, the UK became the largest contributor to the HLHC program. And also energy recovery for colliders that I will come back to later. Now, here's one more advertisement for the prowess of colliders. So many of the heavier objects of the standard model, heavier elements of the standard model were discovered at particle colliders. As you may well know, The Spear co-discovered the charm quark and discovered the tau lepton. Petra discovered the gluon. Sorry, the SPP/S, of course, W and Z bosons, and then the tevatron top quark and the LHC, the Higgs. So all these elements were discovered at colliders. Also interesting that all the elements on the left side, all the spin 1/2 particles here on the left side, they were discovered in the US, and all these integer spin particles were discovered. The force carriers and the Higgs were discovered in Europe. Okay, John already alerted you that there are still a lot of unknowns and that we need to explore further to address these questions. Dark matter, dark energy, also the other questions related to QCD, quark-gluon plasma, etc. So we need new colliders. One more slide on the general. You all know reaction rate is cross-section times luminosity. Oops, my God, too much animation here. Anyway, this is a basic equation for luminosity in terms of collider parameters as a beam size at the collision point, horizontal and vertical beam size, the bunch population square, and the collision rate, basically. And here you see the progress in peak luminosity over 90 years. Also tremendous progress, 8 orders of magnitude in peak luminosity improvement, or 7, sorry, actually 7 or 8 over 60 years. Now the present state of the art is represented by the Large Hadron Collider, circumference 27 kilometers. We have 4 collision points where the 2 counter-rotating proton beams cross. There are 2 high luminosity experiments, 2 secondary experiments. It's of course the highest energy collider. It runs extremely well. Peak luminosity is up to 2.2 10 to the 35, and they need to be leveled to 1.5 10 to the 34 because so far the experiments could not handle higher peak luminosities due to a very high pile-up of events. Here's run 1 at relatively 7 to 8 TeV center of mass. Run 2, integrated luminosity evolution. Run 3 has just started this year and already exceeded the goals in integrated luminosity for this year. For E+ E- machines, the Super KEKB in Japan, circumference about 10 times smaller, 3 kilometers. It has the world's highest luminosity and smallest beta function of all electron-positron colliders. Something missing here. Anyway, you can see the very small beta function. It's at the moment 8.8 millimeter, which is much lower than any of the previous colliders had. And I also introduced a new collision scheme, which is called the virtual Crab-based collision scheme that was originally developed for FCCE in 2015 and in 2020 installed in implemented at Super KEKB. So you can see they had several runs, not too many runs, actually a lot of downtime in between, and each run achieved a new world record luminosity, actually, as you can see here. So at the moment, the record is 4.7 10 to the 34, and they accumulate about half an inverse autobahn over 3 years of operation. So this is the plan for Hi-Lumi LHC. So there is a run plan at least until the end of the 2030s, perhaps until 2041, 2042. And the goal is to accumulate more than 3 inverse autobahns. So about increase the integrated luminosity by about a factor 10 to what has been achieved so far. And this long shutdown 3, at the moment, it ends somewhere end of 29 or so. Sorry, no, end of, I don't know. Yeah, I think. Sorry, end of 28, perhaps. So near future collider is the electron-ion collider. I guess we will hear more about this from Ferdinand. That is approved, under construction, and we should expect first collisions around here. I don't know, around 2031, 2032, perhaps. And also, sorry, luminosity can reach 10 to the 34 at the center of mass energy. Okay, then we had the SNOMAS process in the US during 2 years, which had its final meeting in Seattle this summer. And it was pointed out that to make progress on the energy front, yeah, we need higher energy, and we also need higher precision and higher luminosity. So there's the Higgs factories, which improves the sensitivity, and there are future high energy colliders which go to higher energies. For the hadron colliders and higher energy colliders, there are 2 proposals. At the moment, there's the FCCHH, already mentioned by Jean. It's now about a 91 or 90 kilometer circumference machine with 8 surface sites and up to with 4 experiments like the LHCs here in a symmetric configuration. And And then there is a counterpart, which is the SPPC. Recently, I think, changed to CPPC, the name in China, which is a complement of, each of them is a complement or second stage of a proposed E plus E minus 6 factory. So this is similar. This is based and connected to the existing CERN complex. So the LHC or superconductor SPS could serve as an injector into the FCCHH, while the Chinese project is a complete greenfield machine, and they need to also build the entire injector chain. And then for the E plus E minus 6 and electroweak factories, there are many more contenders, at least presented to SNOMES. There's a well-known ILC, where we are waiting for a decision from the Japanese government to go ahead. There is a CLIC project at CERN. Then now there is a C-Cube, a cool copper linear project promoted by SLAC. There is HELEN, which is a kind of advanced ILC with higher performance superconcavities, which would fit on the Fermilab site. And then there is there's FCCE already mentioned, which is, and the CEPC. These are circular colliders similar to super KEKB, but at much higher energy, and also even at the Z, they can run from the Z pole up to the top quark threshold, and at the Z pole, the luminosity is even higher than the super KEKB luminosity. And then the energy recovery linear-based machines, two are shown here. Actually, there are three, but the two are linear collider-based energy recovery machines, RELIC and ERLC. And then there is a CERC, which is the circular version of the energy recovery version of the FCCE or CEPC. Okay, there are many topics I could discuss. Here I give you some feeling here. High field magnets we need for the higher energy machines, and for the muon colliders, we need superconducting radiofrequency systems, especially for all the E plus E minus 6 factories. We need efficient RF power sources for sustainability. We need to produce enough positrons. The higher the luminosity, the more positrons we need to produce. There's other ideas like a gamma factory. I come to this, back to this later. There's monochromatization to measure directly the electron U-cover coupling at the circular E plus E minus collider. Energy recovery Linux mentioned. There are also gamma-gamma colliders, which could be add-ons to the linear colliders, muon colliders, advanced accelerator concepts, and the issues of sustainability. So here's a picture of the high field magnet development. There's some color code. So red means operation at 4.5 K or so, and the blue means operation at 1.9 K. So blue is cold, and 4 is relatively warm. And then if they have open triangles or circles, there's an aperture for the beam. Sorry, these triangles actually are used in operating machines, and the circles are prototypes. And if the circle is not filled, then it means there is an aperture for the beam. And if the circle is filled, these are magnets without any aperture. Anyway, you can see some progress over 40 years from fields around 5 Tesla used here for Tevatron, Hera, etc., even to fields of 8.3 Tesla for LHC. And then for the future, these developments go to field levels of 16 Tesla based on Radiofrequency tin superconductors. And there are several. There's Fresca-2 and RMC at CERN and ERMC at CERN. And there's a Fermilab MDPC-T1. So maybe there's some picture. Anyway, the CERN high field magnet program looks like this. This is the present state of the art. This is the total magnet length produced on a logarithmic scale. As for LHC, set this scale here. So we have more, 20 kilometers of 8 Tesla magnets. And then the Hi-Lumi LHC needs a few hundred meters of 11 Tesla quadrupoles and dipoles. And then these prototypes, which come to about 15 Tesla. So the CERN high field magnet program aims to go in different directions. We need more robust Radiofrequency tin over extended lengths for the Hi-Lumi LHC projects. Then we develop 16 Tesla in larger quantities for possible FCCHH. And then there's another path for FCCHH, which is to go to HTS, which could reach higher fields, but could also allow operating at higher temperature. That would be very much advantageous in terms of energy efficiency to go to higher temperature magnets. Okay, sorry. Here were some pictures. These are the CERN magnets which reached this ERMC reached actually 16.5 Tesla, but it has no aperture for the beam. And Fresca-2 has an aperture reached 14.6 Tesla. And this is a Fermilab counter. But this is a cosine theta magnet which reached 14.5 Tesla at Fermilab. We can also maybe learn from our colleagues in the fusion business. Here, for example, there's a HTS magnet built by MIT, 10-ton magnet, which reached a 20 Tesla. So this indicates that there's hope that we could use HTS also for the next generation Hadron Collider. I think that would have many advantages if that could be done. Now looking at the superconductor IF, there's been great progress thanks to the Tesla collaboration and Tesla ILC developments, and many projects actually have profited from this. This plot shows exciting gradient over time, again 60 years. A lab operated with a few megavolt per meter still, and you can see the progress that has been made. Single cell cavities are well above 50 megavolt per meter or so, and this has allowed many projects, CBUF, LCLS2, XFEL, etc. And then many other projects are profiting from this development. So there is progress in both directions: higher gradient for higher energy machines and higher Q factor, which allows lower cryogenic costs. Both of this is important also for the FCC. And some of the new ingredients, nitrogen infusion and nitrogen doping, have allowed to reach Q values of several 10 to the 10 and reach gradients well above 30 megavolt per meter. So there's been enormous progress in the field in SAF, and I know that in particular in India there is a lot of activity in this field, and we hope maybe that we can collaborate. This shows just a summary, very complex table for the FCC ERF systems. We will operate at 4 different energies in the base and on the Z, at the W, Higgs, and TT bar, and in total we need about 336 cryo modules, mostly 800 megahertz and also 400 megahertz. Here are all the parameters. I think this is rather similar to the cavities that are being built in India for PIP2. Let's see. Okay, we also hope to have more efficient RF power sources. And that seems after 80 years after the invention of the Clyson by the Varian brothers in Palo Alto, there are some new ideas pushed by Igor Sirachev and collaborators, where we hope that we can push up the Clyson efficiency from 65% levels up to 80% or higher. And this will be quite important for a machine like FCCE, where the RF and the RF power is one of the dominant factors in the design. Okay, so there's another project proposed at CERN to reuse the LHC as a so-called gamma factory. So the idea is to accelerate and store partially stripped heavy ions, so lead plus 81 instead of plus 82. So there's a lead ion with 1 electron attached, and you can accelerate. This was demonstrated in 2018. Such a beam was accelerated and stored, and the beam lifetime at top energy was 38 hours. You can collide with a laser and excite electronic transitions of this electron, and then the LHC works like a frequency converter. So we have the laser frequency, and this excited electron decays again, emits a photon, and we get X-ray bursts with the energy or frequency which is shifted by 4 gamma squared compared to the initial laser frequency. So this is a very efficient converter of laser light into X-rays. And the prediction is that we could use this to get 10 to the 16 to 10 to the 17 positrons per second, but also very high fluxes of pions, muons, etc. And one can use this laser interaction also for a cooling of this ion beam. And there's an alternative path to high luminosity LHC using laser-cooled isoscalar ion beams. So I think this could be quite interesting future use of the LHC after the end of the high-lumi LHC program. So here's a view of Vitek Krasny, who proposes this for lots and lots of applications. And one interesting application is to use the gamma factory as a driver of a subcritical nuclear reactor, using the photons at a specific energy to convert very specific isotopes from unstable isotopes into stable isotopes. So this could be very tailored, and this machine is quite efficient because RF power is converted 100% into the X-rays. The only inefficiency comes from the cryogenic system, so that the total efficiency is about 20%, is much better still than for any proton-driven waste transmutation or ADS exciter driver. So anyway, this is quite exciting. This has just started this year in collaboration with colleagues in Japan and China. Okay, monochromatization, I mentioned briefly. FCCE would allow to measure the U-cover coupling directly at 125 GeV center of mass. To do that, we need to reduce the effective energy spread of the collision. This can be done either by creating dispersion at the collision point, and we like to do this in horizontal plane because we also need to cope with the Beamstrahlung at the high energies, which is synchrotron radiation emitted in the collision, which is mitigated by a large horizontal beam size. So horizontal dispersion, non-zero dispersion is good. We can do it with or without crab cavities. An alternative scenario proposed by Pantaleo-Raimondi is to introduce a chromatic wave shift. And for this, we don't need any new hardware. This can be done in the operating machine. Okay, now I come to energy recovery. It was proposed first by Mauritiner in 1965. He also, when he proposed the first linear collider, he said at the time that linear collider makes sense only with energy recovery. And then also later proposals, that was a low energy collider, a few GeV collider. In 1976, Amaldi and others proposed already 300 GeV collider, also based on energy recovery, otherwise very similar to present-day linear collider proposals. Now we have many more proposals. Actually, first there was LHE, there was the electron-ion collider from Vladimir Litvinenko, Thomas Rosales, and then the LHEC we started in 2006, around 2007, and actually Swapan came to CERN and he proposed to use energy recovery to increase the luminosity of this collider. And recently, and then also we have FCCEH, which is add-on to the FCCHH, which would also use energy recovery to provide the electron beam. And then recently we have these new proposals, CERC, which is a Higgs factory based on energy recovery, and two linear colliders. This is the one from Telnov, and this is a Litvinenko proposal. They need also RF, SRF with very high Q values of the order of 10 to the 11 Q. On paper, these machines, they work extremely well. Here's FCCE, which is very outstanding, up to a few hundred GeV. If you believe the IRL proposal, you could get even higher, much higher luminosity and go even to much higher energies. Here's also click and ILC luminosity somewhere here. This is a plot that was also presented at the SNOMES process. Okay, now for the energy recovery, there's the landscape is shown here. This is beam current, this is energy, and these straight lines, diagonal lines here are constant beam power for applications. And there are completed machines in red, ongoing cold and warm machines in green, and in progress and proposed in blue. So now I can say that the Swapan contributed to many of these machines, the first demonstration at CBAF and also the JLab FEL. And then he came to the UK and made the first ERL in Europe with the Alice. And now, and then he, as I said, he proposed LHEC. Oops. And then all these other machines, they have similar power, linear collider, ERL, even a 10 gigawatt or up to each edging towards the 100 gigawatts power level. Okay, there is a prototype machine proposed for a multi-turn ERL that should demonstrate feasibility of the LHEC. This should be constructed in Paris at IISc lab. This is the configurations that would go, I don't know, maybe maximum a few hundred MeV or so. Okay, muon colliders. Muon colliders are attractive since the muons emit much less synchrotron radiation and they have no Beamstrahlung in collision. And there are two different production schemes proposed. There's a proton-driven muon collider, which generates muons by hitting protons, sending protons onto a target to produce pions, which decay into muons. And then the muons have a huge emittance and fill a huge phase space area. So you need a fast cooling, ionization cooling, before you quickly accelerate. Alternative proposal is to use positrons, annihilate protons against electrons at rest, and then you don't need any cooling, and you need against fast acceleration because the muons are unstable and decay. So muons decay within a few hundred to 1,000 turns. The number of turns that they can survive only depends on the magnetic field. So we need very rapid acceleration, and at very high energies, the muons that decay emit neutrinos, which could also interact with matter, and this becomes a problem at very high energy because this neutrino flux goes up as maybe as a third power of energy also. So above a few 10 or a few tens of TeV, the solution is somewhat unclear. Anyway, the target design is very interesting and challenging for the muon colliders. Here's an example for a proton-driven target. There's proposal to have the this target, which I think is graphite, held at a 2000 centigrade, and it's immersed into a solenoid of 20 Tesla field or so. So extremely challenging targets for this proton-driven muon collider. And for the positron-driven muon collider, we propose a plasma target where we have basically no nuclei, and the positrons interact with the electrons from the plasma and annihilate against those. That's probably the most optimum situation. And then we could somehow attach a muon collider to the FCC LHC CERN complex. Okay. I didn't tell you there are two other Higgs factories proposed, which is gamma-gamma type of colliders. One is based on the warm, cool copper LINAC, and you also use the same LINACs to drive FELs, and then you collide the photons generated in these FELs with electrons coming from the other side. This is called XCC. This is a proposal from SLAC. And there is a proposal also from Fermilab for high energy, high luminosity collider. Interestingly, the SLAC proposal operates with an Compton X parameter of 1000, while in earlier designs, we always try to stay below X of 4.8, above which you have pair production. Now, this pair production problem here is avoided with very high polarization of the electron beam and the laser. By having the right polarization, you can go to very high X without this problem. Okay, now advanced accelerators are plasma colliders, which have very short wavelengths. This plasma here, for example, this plasma bubble is about 35 a few tens of micron in length, and the typical electron density, I don't know, I cannot read it, 10 to the 18, maybe inverse centimeter cube. Anyway, there is a demonstrator facility under construction and approved in Frascati, which should go into relative energy spreads of the order of 10 to the -3, which will be outstanding for a plasma accelerator and reach energies of a few GeV. And that could be a step forward towards higher energy application. This is the timeline of this Eupraxia project. Operational phase should start in 2028. And commissioning, decommissioning is already scheduled for 2062. Plasma accelerators have one problem that we also, if you want a collider, we need to accelerate positrons, and to accelerate positrons in a plasma is much more challenging. So there are some configuration with multiple lasers. So here is a central laser and a donut-shaped laser pulse superimposed, and this combination somehow can trap some positrons in between these different laser bubbles. It's relatively complex. I think this needs more work. Beam quality from a plasma needs work, but acceleration of positrons needs even much more work. Now we had a study on different advanced accelerators as the plasma wake field acceleration, which is beam-driven, laser wake field acceleration, which is a laser-driven plasma, and then the dielectric laser accelerators, which is a laser feeding into a dielectric structure. This is quite interesting, actually, because in this dielectric laser accelerator, we can have much higher repetition rates. For example, here, this example from this European strategy process is a 20 megahertz repetition rate of bunches. So recently I started a small program in the frame of the IFAST EU projects with the EPFL and PSI colleagues to look into dielectric laser accelerators as accelerators to explore the dark sector. And we have some first results. So this is just an example of a dielectric laser accelerator from the literature. You shine a laser onto the structure and you can accelerate an electron beam. And you can also, depending on polarization and the phasing, you can also get transverse deflecting cavities here. Anyway, this is a dark sector experiment. This is proposed at SLAC. LCS2 is called LGMX. They aim at the baseline at 4×14 electrons on target at 4 GeV. And this is the baseline in blue, and then there are possible upgrades with higher energy of LCLS2, etc., and more electrons. Now with the dielectric accelerator, we can do the same or more. We need, as I said, very high repetition rate, and this can be achieved if we make the structure part of the laser. This is an old idea of Bob Zimmermann, recently revived. So if we can have the structure be part, we can have very high repetition rates. We need about 10,000 of such structure lasers to go to 10 GeV energy. And then we could have also deflecting structures to illuminate with single electrons different portions of a detector. Anyway, this looks quite interesting. We could go on paper even up to 10 to the 18 electrons on target. Okay, now I come to the ultimate limit. Ultimate limit to magnetic acceleration is a Schwinger critical field where the vacuum breaks down. So this field corresponds to 10 to the 12 megavolt per meter or 10 to the 9 Tesla. If you want to go to the Planck scale, which is 10 to the 28 eV, we need the accelerators, which are, and we operate exactly at this threshold field. We need accelerators of the size of 10 to the 10 meter. And actually, depending if it's linear collider or circular collider, it's about the same size in either way. We need about 10 to the 10 meter dimension, which is 1/10 of the distance between Earth and Sun. Okay, thank you. And actually, this was studied by colleagues at SLAC in 1998. Pisen Chen and Bob Noble, they wrote a paper and they concluded this is not an inconceivable task for an advanced technological society. So maybe we should think about other ways. Perhaps we should use a gravitational force to go to the Planck scale. But anyway, I suppose that this is our goal. Some time ago, I was contacted by a colleague from Atlas, James Beecham. He asked me if we can make a collider on the moon. So I said, yes, why not? So we developed some parameters for a collider going around the moon. I think Enrico Fermi proposed a collider around the Earth. The moon is somewhat less ambitious. So anyway, we made some parameters. We need about, to power this collider, we need about 1 per mil of the sun power incident on the moon surface to power a hadron collider going around the circumference of the moon. Anyway, this was actually published. I was told that the CERN director of research almost fainted when he saw this paper. But anyway, it was published in the same week when The Economist had a headline, "Everyone's going to the moon, a new space race." So that was an interesting coincidence. Actually, the Americans, also the Japanese, and others have quite ambitious plans to build some bases on the moons and to also, because this accelerator actually should be built based on material sourced on the moon itself, rare earths, etc. Maybe many elements needed could be available on the moon. Anyway, I see also India has a moon program. That was just in news last week, so maybe this could be interesting. But probably we need to think for a more efficient way to go to the Planck scale. Now I come back to the next generation. These are all the contenders for the next generation Higgs machines. And they were the center of mass, energy, luminosity, years to first physics, electrical power. So they all need a lot of electrical power. And they all cost in the order of $10 billion or more. This is the efficiency, luminosity per wall plug power on a logarithmic scale. And for these mature projects, actually FCC is the most efficient by far in this low energy range up to the TT bar threshold. If you go above TT bar threshold, linear colliders become more efficient, ILC and click. And for multi-TeV, muon collider is the most efficient machine. Recently, some colleagues published a comparison and they calculate energy consumption and carbon footprint per Higgs. And no surprise, this is actually Patrick Janot and Alain Blondel, they published this. And actually, energy consumption per Higgs is the lowest. Thanks to the high luminosity, evidently, it's the lowest for CEPC and FCC. And if you put in the carbon footprint of the electricity in the different countries, and actually France and Switzerland, they have a very low carbon footprint of the electricity. So this brings this carbon footprint per Higgs down to very low level. Okay, then other considerations, we need to go to higher temperatures for Hadron Collider. This shows cryo efficiency as a function of temperature. At the low and at the 1.9 K or 1.8 K, it's extremely inefficient. If we could go to HTS materials at, for example, 20 K, it would be much easier to extract synchrotron heat from a future Hadron Collider. And also we need to cope with energy fluctuations if we use renewable energies. This is from, both of these are from an IPAC talk from Mike Seidel. Then as I said, we need a lot of positrons. Surprisingly, that the ERL machines, which have much higher luminosities, they claim they need much less positrons. I think that needs to be revised because it's probably impossible to have a high luminosity without producing enough positrons to consume. Okay, so for the positrons, we are developing a new source also with an HTS element, HTS solenoid. It's a prototype source for FCC, and that should be tested with electron beam at the Swiss FEL. The test is planned 2024-25. We expect with this new type of adiabatic matching device using the HTS solenoid that we can get up to a factor 3 higher positron yield compared to conventional sources. Okay, then finally there's a maturity comparison from SNOMES. So ILC is shovel ready, as I say, up here. The 10 click is also very mature, and FCC and CEPC come here next. And many of the other concepts, they need a lot more development. Okay, so brings me to the conclusions. There was great progress in the superconductor RF and in high field magnets over the past 40 years. The accelerators and colliders are getting ever more efficient. There are synergies with other applications and other fields, for example, with the fusion developments. And there are numerous innovative concepts and challenges for future colliders, including gamma factory and monochromatization and energy recovery. And I propose that we study more the DLAs for indirect dark sector searches. Sustainability has become more important, and several promising paths forward. And the future depends on what we do in the present. So let me conclude with some pictures from our past colliders. So thank you very much.
Thank you, Frank, for this very comprehensive coverage, accelerator overview, and with proposals to go to the moon. Sound very exciting. Okay, we have a few minutes for any questions or discussion. Rohini.
Can I come back from the moon to the ground? I wanted to know for the HTS developments, what are the areas? I mean, these are really material science developments, or where is the real direction in research, pure science research that would feed into HTS to reach the 20K that you are talking about? So what is the core area where research has to be focused?
The core idea. I don't know. I think in Europe and in China we focus on different HTS materials. I think in Europe normally we look at the Repco or things like this, and in China they look at the iron-based superconductors which were discovered in Japan in 2008. So they want to make their hadron collider fully based on HTS. But I think recently we look at HTS as possible lower field HTS for the FCCE. So we have already, I showed you the solenoid for the positron source. We also have a design of HTS magnets for the final focus. We need very strong sextuplets. They could be made based on HTS, also the final quadruple potentially. And then we have a project with the PSI to look at whether we can replace all the quadruples and sextuplets of the collider with HTS magnets. These are rather low field, but it could be a good step towards the high field HTS for the next hadron collider.
Because I have been listening to some of the CEPC people, presentations and their plans for SPPC.
Yes.
And they, as you just now said, that their HTS is a more iron
base. Yes, they have very ambitious R&D program in China with many different companies.
It's impressive, actually,
yes.
When I heard them. So what I was really trying to think is, or question that I wanted to ask is that, is there something that we can ask our materials people, people who do material designing and so on and so forth?
I think that's a very good question.
Some focused research that we can ask them for. I mean, I have no knowledge, but just this.
I think it's an excellent question. Maybe we should discuss with some magnet people at CERN, and maybe also with Lucio Rossi, who is back in Italy, but he has always promoted the HTS magnet development, and he is still pursuing that.
Yeah. So I was just curious whether we can employ the solid state and condensed matter people in the game to see whether you can tune the materials somehow.
I think it's probably the answer is yes, but we need to discuss. We have to find the right people to give us inputs.
Yeah, because the advantages are so many from your curve there.
Yeah.
Thank you.
Very good question.
Yeah, I have a question about this. I think we are still using in LHC the bunch crushing angle, very small angle, but there is a bunch crushing angle.
Mm-hmm.
However, KK, they have already tried the crab cavity for the full overlap.
Mm-hmm.
Is it not possible to, even though we can get 10-20% level of luminosity high, is it not possible to do it in the LHC?
No, this part of the Hi-Luminosity LHC program is to have the crab cavities to restore the full luminosity, or nearly the full luminosity. But for the future E plus E minus colliders, we no longer consider the Crab. Also EIC, by the way, uses Crab cavities. I think Ferdinand will tell you. But for the E plus E minus machines, we have relatively long bunches and we want a very small beta star. And there is a new scheme with a large crossing angle, small beta star and long bunches, and using the so-called Crab-based sextuplets. No cavity, but we change the focus. We change the vertical focus as a function of horizontal position. And that way we can get very high performance and a high beaming tune shift without Crab cavities.
Any other question or comment?
I just have a curiosity about the gamma collider, not the gamma collider, the gamma production by interaction of the laser with the ion beam. How is it different from the inverse Compton scattering of the laser with the electron beam? Like here, what is the difference? Is the cross section more? Or
I think the cross section is much higher. Yes.
Okay.
Many orders of magnitude higher. That's a key difference, I believe.
Okay.
And you don't lose the ion which scattered. The ion survives. You can use the same ion even in the same passage. You can use the same ion several times to emit a photon.
Okay.
And the cross section, I remember, I think it's maybe 6 orders of magnitude higher or something like that.
Okay. Thanks.
Okay, I think one last question. Vivek?
What do you think might be the time scale of a laser-based accelerator to give intensities that are useful?
So the laser-based?
Accelerator.
I mean the dielectric or the plasma or any
Maybe the dielectric one. That's
the dielectric one.
better.
Yeah, I don't propose it for a collider, just to excite single electrons. I want to excite single electrons with a very high repetition rate. So I hope that the time scale is not too long, but I don't know, maybe 5 or 10 years. But I must say that people are talking about this since 20 years and the progress has not been so high, but there is some work. There is a so-called project A-chip, Accelerator on a Chip, which is supported by the Moore Foundation, which is with SLAC and some institute in Europe, and they are developing test structures. So I hope that with this funding, there will be faster progress, but I don't know, probably it's maybe 10 years.
Okay, I think we should then move over to the next talk. But then before that, let's thank Frank once again for a very nice talk. Thank you, Frank.